In this lecture, we're continuing our lecture on isomers, and we're going to look specifically at geometric isomers. Geometric isomers are a type of stereoisomer. A stereoisomer, we see, the atoms have the same connectivities but different spatial arrangements. Again, our definition of isomers, you have the same chemical formula but different structures in some way. We previously looked at structural isomers, where you have the same chemical formula but different bonds. Today we're looking at stereoisomers. So the same chemical formula, the same bonds, but different spatial arrangements. We'll see what that means. And specifically, we'll look at geometric isomers. So ligands have different spatial arrangements about the metal ion. And remember, the metal ion is this metal in the center of the complex. The two different types of geometric isomers we're going to look at are cis and trans and Fas and Mer. Add a couple definitions. For cis and trans, you must have either a square planar or an octahedral geometry, and you need exactly two identical ligands. For Fas and Mer, you must have octahedral geometry only, and you need exactly 3 identical ligands. And we'll look at a couple examples here. So this is an example where we have a square planar geometry. I see the arrangement is square planar because I see my platinum metal ion in the center. I know that is a 2+ ion because I have 2 negative chloro ligands, 2 neutral amine ligands. And visually, I can see this, right? Square planar arrangement, 90-degree bond angles. And what we're looking at in this first case is a cis arrangement. Cis isomers have groups on the same side. And so I see this as cis because I have my chloros in adjacent positions. In this case, it's 90 degrees. And my amine ligands in adjacent positions at 90 degrees. So the same side, which also means if we have square planar or octahedral, that's going to be 90-degree bond angle. When you take organic chemistry, you'll look at cis and trans configurations, and you'll see how you can have a cis configuration where the similar groups are on the same side, but the bond angle is different from 90 degrees. So for our case, it'll be 90. For future chapters and future classes, you'll see that bond angles will vary. Trans configuration, the isomers have like groups on opposite sides. So I can see in this case, I have a trans configuration. My chloros are on opposite sides. In this case, that's specifically 180 degrees. And my amines are also at 180 degrees. So again, for square planar or octahedral, trans will be 180 degrees. In organic chemistry, you'll see that bond angle will vary. Let's look at one other example for cis and trans, and this will be an example with a octahedral geometry. So for example, if I have the chemical formula FeCl2H2O4. Let's correct that. H2O4. And this is a neutral complex, so I actually don't need these square brackets. I see that my structure is octahedral because I have 2 chloros and I have 4 waters, so my coordination number is 6. So that means I have an octahedral geometry. I know I have cis and trans isomers because I see I have 2 of the same ligand. I have 2 chloro ligands. So let's draw this. Iron is in the center. I always draw my octahedral template first, line, line, wedge, wedge, dash, dash. And let's look at my cis configuration. So the chloros will be on the same side. So I put the 2 chloros there, but realize it could be any 90-degree angle. So I could have a chloro here and here. I could have, let me mark those. I could have chloros. This would be cis. I could also have this as cis, right? I could also have this as cis. I could see this position cis. So as long as they're adjacent to each other, right, this could be cis. There's many, many options for what to draw a cis configuration when you have an octahedral structure in 6 different locations. Again, the only requirement is that they're at 90 degrees. So let's go back to just these chloros. So I see that they're cis. I'm putting them at 90 degrees in those positions. All other ligands are aqua. And I know that aqua oxygen is the donor atom. And so I draw it like this. I also have a trans configuration where my chloros will be at 180 degrees. Start with my metal center, line, line, wedge, wedge, dash, dash. Again, this is how we represent 3-dimensional drawings on a 2-dimensional plane. And now the trans, 180 degrees. So I drew that as trans. Realize you could also have trans. Those positions would be trans from each other. These positions would also be trans from each other, so several choices. I'm picking just this, the 2 bonds that are within the plane of the page. And now we're going to add our aquas. I'll erase these dots. They are not needed for this structure. So our aquas, O is the donor atom, so that's the atom that must be touching that bond. So here I see 2 different isomers. Cis, the same groups, the 2 identical groups on the same side of the structure. Trans, the 2 groups are on opposite sides of the structure. So trans, think larger bond angle. Cis, think smaller bond angle. One useful example to look at, if I have a tetrahedral structure, no cis trans is possible. So let's talk about that for a second. So if I have my metal in the center, and we'll just do a generic metal, M stands for metal, my tetrahedral structure, and let's say I've got 2 chloros, and I want to put them cis and trans, and then we'll just call the other ligands X, Y, doesn't matter what they are. So in this position, my 2 chloros, I know this bond angle is 109.5. And if I want to have cis-trans isomers, I know I need to have different bond angles. And if you remember from our tetrahedral discussion, all of these bond angles are 109.5 degrees. So if you have if you first put the 2 CLs at 109.5 degrees, there's no way to move them to a different position and have it a different configuration. No matter where you rotate those chloros, you could just rotate that molecule in space and you would have the identical structure. So this is one good topic to understand, and that's why when I was going over cis and trans geometries, I only spoke about square planar and octahedral. The next geometric isomer we're going to look at is FAS and MER. So FAS and MER stands for facial and meridional, and this isomerism is only in octahedral complexes where we have, of course, our metal center, and then we need 3 identical ligands. And in this case, I have 3 chloros and 3 amine ligands. This first structure is our FAS configuration, or facial. And here we have all 90-degree bond angles. So if we look at the chloros, I can see these are all at 90 degrees. And the amine groups are also all at 90 degrees by default. If you have 3 groups at 90, the other 3 must be also at 90 based on the geometry of an octahedral structure. The reason this is called a facial structure is because if you were to cover this octahedral structure in paper mache or cover the outsides, you would see that that facial arrangement, it takes off on one face of the octahedral structure. Our other example here is MER, which stands for meridional, and we have a 180-degree bond angle and a 90-degree bond angle. So I can see my chloro groups, 180 and 90, and my amine groups, 180 and 90. And I think about MER, like meridional, like the prime meridian in the globe goes all the way around the globe. If you look at the arrangements of these, you can see how that goes around like this outsides of that octahedral structure. Let's look at one more example of a FAS-MER isomerism. And in this case, we're going to look at the chemical formula. In this example, we'll look at the chemical formula Cu BrCl NH3, lots of different ligands, H2O3. And there's no charge on this, which means my copper must be 2+, since I have a -1 bromo ligand, a -1 chloro ligand, neutral amines, and neutral waters. I see that my coordination number is 6, because I have 6 donor atoms, bromo, chloro. The N from the amine is the donor atom, and O from aqua, 3 of them, is the donor atom. So I have an octahedral structure. The reason I recognize that I have FAS-MER isomers is because I have 3 H2O ligands. So let's go ahead and draw these. I always start with my metal center, Cu, line, line, wedge, wedge, dash, dash. And let's start with the FAS isomer, all 90 degrees. And my waters are going to be FAS, OH2, 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 all at 90 degrees. I could also have chosen to put them in this position, 90, 90, 90. I could have also had 90, 90, 90. Okay, so there's many different 90, 90, 90 configurations where they're all at 90 degrees. So there's not only one right answer for these structures when you draw them. And then we need to go ahead and add our other ligands. So the other ligands that I have, doesn't matter where they go, bromo, chloro, and amine. So again, FAS, because I have my 3 identical ligands at 90 degrees. Now let's look at the MER structure. I know I need 180 degrees and 90 degrees for my 3 identical ligands. Copper in the center, line, line, wedge, wedge, dash, dash. And again, there's many different options for where to put these at 180 degrees. So again, 180 would be here, or here, or here. I typically start with my 180 with the bonds within the plane because that's just the easiest for me to see. So I'm going to do OH2, H2O, again emphasizing that O is the donor atom, really important. And then the last water can go in any of the other positions because they're all equivalent. They're all within that square plane of that kind of center plane of this octahedral structure. So I'm going to go ahead and it's right there, OH2. And now we add our other ligands. I've got a chloro, a bromo, and an amine, N as the donor atom. So again, this is an example of fast-mer isomerism. You need to be able to look at a chemical formula and recognize what type of isomers exist. So we have to remember fast-mer isomers exist. First, you must have an octahedral structure. If it's octahedral structure, go ahead and see if you have 3 identical ligands.